Hey everyone, I'm William Falcon. I'm the creator of Pytorch Lightning and the co-founder of Grid.ai. And along with Sean Nairth today, who is one of our research engineers at Pytorch Lightning and is doing incredible work at helping Lightning scale up your models. So today we're going to talk to you about Sharded and how to apply it to getting models to train at scale. So if you've tried to train at scale, across many GPUs or many nodes, you know that there are a lot of challenges. So we're going to cover three things today. We're going to teach you how to do training at scale with Pytorch Lightning. Then we're going to talk about distributed training. And then we're going to talk about sharded training. So how do we train large models longer and faster? You have to overcome three bottlenecks. The first one is speed. The second one is memory. And the third one is the actual implementation. So speed is very critical when you're going through the model iteration process. So you have an idea, you have some data, and you want to use machine learning or deep learning to get something out of it. The faster you can try ideas, the faster you're going to find results. So let's think about solving a problem. And if you think about this kind of random walk process where you're going to try things and eventually you're going to find something that works, well, it's going to be a sequential process if your training is too slow. That means you're going to try one idea, tweak it a bit, try another idea, tweak it a bit, try another. And that process is going to continue until you're hopefully at a place that you can productionize a model or publish a paper. Higher memory capacity means you can have more parameters and more data on memory. So your batch size can increase and your model size can increase as well. And we know that model size is very correlated today with really good performance. And unfortunately today, you have a lot of things that take up memory. So you have your actual model weights, you have the optimizers, which can store copies of the weights as well. You have the activations, you have temporary buffers, parameters. It really adds up. And you end up using a lot of your memory for overhead instead of actually the data or the weights themselves. And finally, this is really hard to pull off. You need a lot of esoteric knowledge to get every single detail right about distributed training. And that's a lot of what our team focuses on. We spend a lot of time doing this so you don't have to do it. And the problem with doing this at scale is that if you miss one single thing, your model will be a little bit slow, things may not converge. So you spend months just getting all the details right before actually getting something to work. So that's really where Pytorch Lightning comes in. Lightning makes coding neural networks very simple. So here's an autoencoder, and you have basically four methods you care about. The init is where you instantiate your model, or you can pass it in if you want as well. The forward is anything that you want to use for inference. The training step is the core logic, right? So it's everything that's going to go inside your training loop. And then the optimizers method basically lets you define what optimizers and learning rate schedulers are going to be tied to this model. What's really cool is that everything's self-contained, which means it can run on arbitrary hardware. So you can run on 1 GPU, 10 GPUs, 200 GPUs, CPUs without changing a single line of your code. Lightning is really designed around four principles. The first one is self-contained models and data. So to show you the value of having self-contained models and data, take a look at this example. I have 3 models and 2 different data sets. Because everything's modularized and self-contained, I can mix and match them as much as I want. A good test to see whether your model is self-contained is whether you can drop it into the Lightning trainer and it'll just work. The second one is modular code standards. So let's take a look at your deep learning code. Imagine every one of these lines is a line of code. So we're going to factor out your code into 3 parts. The first part is going to decouple the research, and that's going to live in the Lightning module. This is where you want to spend 99% of your time. The next part is to decouple the data, and this is going to live in the data module. And the data module encompasses the data loaders, the transforms, and everything you need to make that data set self-contained as well. And then everything else that is left is going to be automated by the trainer. So this is the boilerplate that most people get wrong, and there's a lot of surface area for errors as well. And the final principle is full flexibility. So I had been using many machine learning frameworks for a few years before I started working on Pytorch specifically. And something that I really cared about, as I was doing research and also putting things into production, was the ability to customize code. So what I didn't want to end up doing was getting onto a framework, it's easy to get on, and then 6 months later you find out that you're blocked because something is no longer accessible. So I wanted to make sure that at the DNA of Lightning, it was this ability to be really, really highly flexible. So how does Lightning do that? It's by giving you this access to hooks. So anytime you want to access any part of the training loop, you're able to just kind of plug into a hook and do what you need to do there. So once you convert your code to Lightning, you get a lot of features out of the box. So some of the most basic features are different accelerators. So you can train on 1 GPU, 8 GPUs, 256 GPUs. You get automatic organization for your artifacts. You get checkpoints, you get logs, you get everything you need to be able to do productive research. You get profiling, many different profilers. But more importantly, we test across many different versions of Python, all the different operating systems, different versions of Pytorch as well, and across different hardware. So we test on single GPUs, multiple GPUs, CPUs, etc. So basically, you can rest assured that the area of code that Lightning automates for you is tested really well, which means that you should really only be focusing on your code. So as I mentioned, accelerators are some of the most basic features and most powerful as well. But we offer many other things such as 16-bit precision, stochastic weight averaging. We'll talk about sharded soon, distributed data parallel, many ways of doing distributed training. You can plug into any kind of way that you want to do distributed training through our accelerator API. So you can plug into any kind of clusters you want, come up with your own new way of doing distributed training. And it's very easy to integrate. We also offer, obviously, early stopping, debugging. You can export the Torch script to Onyx. We automate truncated backprop for you. We do quantization. We do model pruning. So all the latest techniques that are coming out, our team implements them within days. But more importantly, we have over 400 contributors from top labs across the world, PhDs, professors, research scientists in industry, academia, who are all doing their work and putting all of their energy, who are coding things not just for themselves, but for the community. So Lightning is a community-driven project where it's basically the world's research lab. So anyone who wants to do anything can contribute it to Lightning for everyone else to benefit from it. So now I'm going to pass it over to my colleague Sean, who's going to go into details about how to do sharded and scale up your models.
Thanks, Will. We'll be delving deeper into some of the technical details, particularly around training, scaling, and being able to reach those really large parameter sizes. We want to strive for implementations that work not only on those 1,000 GPU clusters, but also to limited compute. At Pytorch Lightning, we work closely with teams to provide the fastest API to enable these optimizations, which have allowed sharded training to be adopted by many researchers. But before we jump into sharded training, I want to ensure we understand what's happening at simpler paradigms. Now, data parallel is a very common procedure that's used by many users. I have one model, and I would like to scale to multiple GPUs. How could I do this? Very intuitively, it makes sense to just scale the data. If I replicate my model across my GPUs and provide a different batch of data for each one of these GPUs, I can scale my training from a data level. And most users are familiar with this. In Pytorch, this is data parallel, or DDP, distributed data parallel, and has become a staple of training, and the elegancy of it makes it very widely adopted. We're going to move a layer deeper, and I'm going to go through a training iteration using data parallel so that we understand what's happening under the hood to give us a better idea of what's happening within sharded training. Now, there's many moving parts when we have a multi-GPU cluster and we would like to train, even for data parallel. So let's start with 2 machines with 4 GPUs in. Now, we have to start with choosing what our rank assignments are, making sure that each GPU and every machine knows where they sit within the world. Now, something that's very overlooked is making sure that we start with the right random seed for each process, and this is something that's handled by Lightning. This is important to make sure that we have the right ranks for data loading, for data splits, and any form of model initialization. We start with initializing our model across all processes. This means the same model exists on every GPU, and this is important. Recall how for data parallel, all GPUs need to have the same model replicated. Now, during our forward pass, each GPU gets a different batch of data or inputs. This is the data parallel piece, making sure that we scale our data across all the different GPUs. And this is what allows us to scale what is called the effective batch size. Through our training process, we pass these inputs through our model, get some form of output, and calculate some form of loss. Now notice how the loss is different for each one of these GPUs. And this makes sense because the data that was received for every single GPU is different. Now during the backwards pass, we will calculate gradients with respect to the local loss for each GPU. So now we can probably see a very crucial point in the communication. If we were to just do an optimizer step for every single GPU now, they will all end up with different weights. So at this point, we have to do some form of synchronization. Now, depending on how it's implemented, this gradient synchronization can happen in a ring or any form of communication pattern, but at the end of it, we're trying to get the same gradients on every single GPU. And this goes through a process of either the GPUs talking together or in some form of cycle. And we end up with the same gradients across every single GPU. Now, a slight mistake here is that we use L1, but just imagine now we have the gradients, the same average gradients on every single GPU. Now, if they were to do the optimizer step, this means they will all end up with the same model. And this sets up well for the next iteration as we continue the forward and the backward process. The benefits of data parallel shouldn't be taken lightly. Here we have a graph from the infamous DeepSpeech 2 paper by Baidu, which really pushed the boundaries of what's possible in state-of-the-art speech recognition. And here they train up to a maximum of 128 GPUs, and this allowed them to reach state-of-the-art results in speech-to-text, paving the way for end-to-end training on very large compute. But what about scaling model size? Data parallelism is great to scale training if my model fits on one GPU, but what happens if my model doesn't fit on one GPU? What if I want to see how big of a model I can train, but I don't really have the memory to really scale this? We start to move towards something called model parallel, a potential answer for scaling our model sizes, reducing our memory consumption, and allowing us to reach further into state-of-the-art results. And it goes without saying the benefits of scale. Recently, we've seen massive jumps in parameter sizes, showing new behaviors such as zero-shot, cross-lingual, and NLP, and we're starting to see similar trends across modalities. Scale will continue to prove crucial, and ensuring we optimize for memory and performance is important. On the flip side, for researchers who do not have access to these thousands of GPUs, fine-tuning these models or even reaching larger model sizes on limited compute is also important to forward research in the community. As we scale these models, it's important that we don't lose sight of the accessibility to research, where compute is limited. Now, these would not be possible, these results you see right now, would not be possible without model parallel or some form of optimized distributed training. And to give us a sense of what makes these results possible, we're going to break down the solutions to scaling that have been used and figure out where Sharded sits within this world and how it could be the solution for training these really large models. We're going to break down these solutions into two sections. Now, both try to target the same problems of trying to reduce memory consumption and scale our model size, but they take a slightly different approach, and we'll step through both, but right now we're going to talk about what true model parallel is. True model parallel is simply splitting your model across whatever available compute you have, normally GPUs. Intuitively, this makes sense and opens up the possibility for larger models. This diagram was taken from a recent paper around mixture of experts, scaling to a ridiculous trillion parameters. And at this scale, you really have to consider splitting your model. Just imagine the amount of weights that need to be stored and iterated through the training process. Now let's delve a little bit deeper into what these ways of splitting are. One way that's very intuitive is to just split the layer vertically. Now, in very particular cases, this can be useful, primarily around embedding layers. So imagine taking a really large embedding layer and cutting it into two and putting one on each GPU. Another one could be some form of very complicated classification task, but at the end of the day, this requires a very specific implementation per layer, but it works reasonably well and stays somewhat elegant. Another way is to split the layers horizontally. So imagine if I have a stack of layers. I can just do what's called a pipeline. So each one of these layers would end up on each GPU. But this gets a little bit tricky because imagine if I have an attention block that's taking much longer than one of my linear layers, I have to start thinking about how would I balance this correctly. And that can be a very tricky task. A lot of manual tuning is required, and even the implementations can be very tricky and dense in terms of boilerplate and code. Now, self-balancing architectures is something that's very highly requested in Lightning, and we are exploring this, but it's an extremely challenging problem. Overall, we're starting to get a sense of why true model parallel is not simple. Now, as you can see from this diagram, there are many ways to split the model, and in many implementations, this isn't automatic. Determining what layers go onto which GPU is an art itself currently. Now, work has been done to try and automate this in the future, and we're looking forward to seeing what is possible in this field. More important, and especially towards accessibility, these implementations are complicated and require a lot of user intervention and tuning. The benefits are incredible and cutting edge, don't get me wrong. However, for a rapid research cycle, this really hinders the overall research project and the application and scale we can achieve on various modalities in research projects, which at Pytorch Lightning is super crucial to us to provide and support. Now, motivated by the difficulties of true model parallel, let's try and find something that's more general, more applicable to a larger set of research projects and modalities. And we'll talk about something I've coined as optimized distributed training. Now, we're starting to realize there's a lot of pain points and difficulty of model parallel. We now know the lack of applicability to a lot of models and research projects, and the complicated code that comes with it to try and implement, and a lot of the user intervention that's required. The DSP team at Microsoft realized that there was a lot of redundancy with how data parallel works when we scale up. And this diagram you see was taken from a great paper that they released called Zero, or Zero Redundancy Training. They asked the question, when we scale our model, can we leverage distributed communication to reduce the memory on each GPU? i.e., can we do something a little bit smarter than just replicating our model across all GPUs? Now, the FairScale team also had this similar idea, motivated by what Microsoft released in terms of Zero, and have been addressing the same question, just a little bit more closer to Pytorch and coining the name Sharded Training. They all have the same idea: can we just reduce the duplication required, and then can we save memory ultimately? And then can we use this memory to either train on limited compute or even scale our model size further? Before we talk about how to solve the redundancy, let's talk about what redundancy there is in terms of memory. Imagine you have a GPU and you would like to train your model. Some of you may already notice that the model itself only takes up a very small portion of the memory, looking at NVIDIA SMI or NVProf. There are many other factors that you have to consider when training a model and take up the rest of your VRAM. Let's take the optimizer states. A commonly used optimizer, Adam, requires storing multiple values for each weight, taking up much more VRAM than the initial model. On top of that, if anyone's using mixed precision, it means we commonly have to store a floating point 32 copy of the weights and parameters. Gradients and activations are also stored. Activations are stored for the backwards pass. Finally, any form of temporary buffers that can store intermediate states also sit on top of your memory usage. And now we see a complete view of why our model, or our large model, cannot train on one GPU, as there's all these other things that need to be allocated. So instead of duplicating everything, or the model, onto every single GPU, a solution to this problem may be, can we partition the model onto every single GPU? So each GPU only has to care about a portion of the model. And why not shard everything? Let's shard optimizer states, gradients, and obviously the parameters. Now, as a solution, this seems very elegant, and it makes sense that every GPU only has to care about a portion of the model parameters. And naturally, we can start to see that if we do this, we reduce the overhead required for each GPU, meaning we can start to scale our model sizes. Now we can see how we can fit much larger models onto our GPU if each GPU only has to care about a portion of the model itself. However, we can start to think about the additional complexity of the communication. If everything exists on different GPUs, this probably means that the GPUs need to communicate much more. So how do we ensure that every GPU remains in sync? We cannot lose too much of the efficiency of data parallel, or will make it far too inefficient to train. To maintain the same performance, we have to consider communication, and we do this in two ways. We can replace the communications with something smarter, knowing that our model is now sharded across different machines. You may recall that before we used an all-reduce step for synchronizing our gradients across processes when using data parallel. Can we do something smarter once the model has been sharded? Secondly, we need to parallelize as much as possible. This means ensuring we fully leverage the machine and the communication bandwidth as soon as possible. Most importantly, each GPU should still receive its own batch of data, and this can be a bit tricky to understand how this could work, and we're going to detail the steps required for this. So firstly, let's talk about communication. The first thing we can do is try and replace the all reduce with something smarter. And we already know now if our parameters have been sharded across different GPUs, we might not need to communicate everything to each one of the GPUs, as only one of the GPUs cares about a particular portion of the model. However, we want to parallelize as much as possible, and the solution for sharded training is to replace the all reduce with something called a reduced scatter. Now, for the sake of this demonstration, let's assume in this diagram that every GPU has access to all model parameters. It's just the optimizer state and gradients that have been sharded. Now imagine we're calculating the gradients for P0. So let's imagine in this step, we would like to calculate the gradients for P0. Now all the GPUs do have access to all the parameters, so that you can all calculate the gradients with respect to their local loss. But when it comes to the actual gradients, only GPU 0 cares about the gradients for P0, and we can use what's called a reduce rather than an all reduce to send these gradients over. This is faster than an all reduce, and means every other GPU that doesn't have to care about P0's gradients can discard them straight away, which saves a lot of memory. However, after all the gradients have been properly averaged and given to the appropriate GPUs, for the next training iteration we still need to synchronize the parameters if every GPU has access to every single parameter. So this is what's called an all gather, where we gather all the different parameters from all GPUs and collate them onto every single GPU. This means that once we run the next training iteration, each GPU will have access to all the parameters and have a synchronized state. Now this reduced scatter and all gather that happens is roughly the same amount of communication that would happen normally during data parallel. Let's go into a couple of the technical details. When we're using Pytorch, we rely on the AutoGrad engine to calculate our auto differentiation. And this happens, or most of the power happens within the backwards pass, and provides hooks to allow us to run these reduce and different types of gradient synchronization steps. One of the great things about AutoGrad is it allows you to do these steps as soon as gradients become available. That means we can overlap a lot of these synchronization and communication with the gradients as soon as they are calculated. This hides a lot of the overhead in terms of communications. And a final technical detail, we can bucket smaller gradients. You can imagine how much communication overhead is required if we just keep passing these smaller parameters. So we bucket them together so that we can do an efficient reduce step, or an all gather. Fully sharded is the same concept, except now this diagram holds true. We split the parameters onto every single GPU, and if we like, even the activations. This does come with a larger communication overhead, as we have to communicate with each GPU in order to get the weights to calculate our forward passes and our backwards. But this gives us a massive improvement in terms of memory and the scale of model we can achieve. Finally, the last concept I'll be introducing today is CPU offloading. CPU offloading is fairly simple. Instead of keeping states, gradients, and even parameters on your GPU memory, why not pass them to the CPU and prefetch them on demand? Obviously this comes with the overhead of host device transfer. However, it allows us to reach these monstrous 1 trillion parameter models on 128 GPUs, as reported by Facebook Research with their release of fully sharded training. We've worked closely with the Fairscale team to ensure seamless integration of sharded and fully sharded training. It is important for us to provide a usable, robust solution out of the box and help the research community use these tools to build larger models and reduce memory usage on limited compute. Here is a typical example of how DDP or data parallel is used within Lightning. As you can see, we just set the accelerator flag to DDP and the number of GPUs and number of nodes. This will automatically spin up any processes that are required and handle any of the orchestration for you, so you don't have to worry about anything or any changes required for your model or your dataset. For sharded training, we've worked very hard to make sure that we have the most seamless and easy to use API in terms of enabling sharded training. And in this case, all we have to do is add an additional flag to enable sharded training. This allows us to shard gradients, shard optimizer state across all your GPUs and nodes without you having to make any changes to your code. We've worked very hard to make sure that sharded is as seamless as possible for the user experience. So what this means is we boiled it down to just an additional flag that needs to be added to your trainer object. This allows you to leverage all of sharded's benefits for the optimizer state and the gradients without, in most cases, having to make any code changes, because a lot of repositories implement ArcPass or some form of API that allows you to add these flags provided by Lightning without even having to touch the code. This allows you to leverage Sharded across a bunch of repos that leverage Pytorch Lightning, including Nemo, which is a very popular library for conversational AI. Coming soon to Lightning, you'll be able to leverage Fully Sharded, which again follows a similar API to what we had for Sharded Training. Now, when we start to scale to really large models, we may need to introduce some code changes. As the model size increases, we may want to start doing things such as sharding our modules or model as soon as they're initialized. For example, if we're scaling to 1 trillion parameters, in most cases this wouldn't fit in one single machine's CPU memory, let alone the GPU memory. So this means we have to consider the global memory pool, not just a single machine. This means as soon as we can, we need to shard our model to leverage the full global capacity of memory. This is very different to the common way, which is where we would instantiate the model per GPU or per device, and then do some form of sharding or just data parallel training. In our case, we would need to instantly shard the model, such that we're able to fit these 1 trillion model parameters into memory. We've already worked with the Fairscale team to try and provide a seamless and frictionless process for this, and we'll continue to make changes and updates to this. Keep an eye out on the Pytorch Lightning documentation for more information in the near future. Recently, I've been using Grid to track my benchmarks when using Fully Sharded, and the modified MinGPT repo I have based on Andre Karpathy's MinGPT. A simple example on training a GPT language model. Now, Grid works from the CLI or the web UI. In this example, I use my Lightning-based code that I push to a GitHub repo, and typically with Python, I'd run a command similar to this to benchmark my model on the server. With Grid, this is extremely simple. All I need to do is swap to Grid Train and add my instance type and the number of GPUs. I could use the CLI to look at the status, but it's nicer to just look at the UI. Here I can track my experiments and see that my experiments have been added to the dashboard. Let's fast forward a bit till the experiment is done. Once done, I can view the metrics logged in Lightning. Particularly the one I care most about is the peak memory during a few batches of training. I could also train directly using the UI to spin up my experiment with its intuitive interface. Now let's talk some of the results and benchmarks that came out of this initially when Sharded Training was released. These results were collected on an AWS instance with multiple A100 GPUs. We require multiple GPUs to really see the benefit of Sharded, but doesn't mean you need to have the most powerful GPUs. All you need is multiple GPUs, so you can start to see benefit with GPUs that offer 7 GB of VRAM on each card. Across the board, we see massive improvements in terms of memory, and this goes across NLP, audio, and vision. Here we have multiple models, from transform models to RNN models, and even ResNet models, showing benefits from Sharded Training, and more importantly with Lightning, a seamless experience when enabling this. Most of these required no code changes for me to benchmark across the hardware. And an important note to make here is that we remain at parity with data parallel in terms of speed. And this is really important because as we start to scale our model sizes up, we don't want to hinder performance too much to reach those really large model parameters. We've been working really closely with the Fairscale team to continue to improve Sharded Training and see even more benefits into the future. With Fully Sharded Training coming soon to Lightning, we see even larger jumps in our model sizes. Recall, Fully Sharded additionally partitions or shards the parameters onto each one of our devices, which brings our memory consumption even lower per device. Here we compared the largest GPT model using the MinGPT repo that we could fit on 8 A100s. As you can see, a magnitude more in terms of maximum parameter size. With even more devices, we'll be able to scale the size even further, and that's how we start to see the 175 billion parameter model sizes such as GPT-3. An important note to make is this doesn't include CPU offloading, and with CPU offloading we'll see even larger jumps in terms of maximum parameter sizes. However, to give a complete picture, we have to start to consider what would be the degradation to our training times. Here we compared the maximum epoch time to the maximum parameter size in a ratio, which allows me to gauge the speed degradation when moving to sharded or fully sharded. We start to get a sense of what the trade-off is between reaching those larger parameter sizes, but the hindrance on the speed and performance. As we can see, sharded maintains a reasonable performance compared to DDP as we scale up these model sizes. One thing to note is we are adding maximum parameter size as a factor in here. So as we're increasing the model size, we still get that benefit of a larger model. However, one thing we can see here is that fully sharded comes with a large speed degradation, and this really comes from the additional communication required to make sure we pull the parameters from the appropriate GPUs in those forward and backward steps. We'll definitely see improvements over time, and the FairScale team are working actively to improve the speed and performance and to make sure this applies to multiple modalities and architectures. But more importantly, it gives us a holistic view of how training time is affected by these techniques. But let's not try and shy away from the idea that we are trying to reach the state of the art in terms of model parameter sizes, so it might be okay to take that speed hit in certain situations. Thank you for listening. If you have any questions, feel free to ask us on the Pytorch Lightning Slack channel or on our GitHub issues. There is a lot more information about sharded training and fully sharded and how to use it in our documentation.